So, hello everyone. My name is Xuanang Chen, and today I will share some about my uh, final project, which is named as Physics-Informed Parameter Identification for Pneumatic Soft Bending Actuators. So, um, basically, my project studies inverse parameter identification for pneumatic zigzag soft bending actuator or some more general soft actuator actuated by air or liquid, the basic fluid-driven actuator made by like silicon or other soft materials like hydrogel. So we incorporated with like a physics-informed neural network to find out its inverse dynamics and kinematics. So the goal is to identify effective stiffness and actuation parameters from sparse displacement and force observations while enforcing reduced order continuum mechanics. And I will first motivate the problem, then explain the model and the inverse PINN, and finally show the baseline results and two formal experiments. So, why is the problem matters? Soft pneumatic bending actuators are a natural application for scientific machine learning because they are compliant, nonlinear, and expensive to calibrate by brute force. And the quantities we care about are not just shape, but also tip blocked force, which is directly related to grasping performance. This motivates an inverse model that can infer effective parameters from limited observations and will be a good guide of finite element analysis. And this slide summarizes the benchmark that I use throughout the project. The actuator is presented as a zigzag pneumatic uh, pneumatic bending actuator with simplified but dimensioned geometry. My three main questions are parameter identification, the value of blocked force supervision, and the data efficiency compared with an MLP. So, this slide shows the reduced order mechanics model used throughout this project. The first equation described the extensive centerline kinematics. X and Y are the centerline coordinates. S is arc length, and theta is the tangent angle. So the second equation is the effective moment balance. EI effective is the effective bending stiffness, and Kp maps the pressure to an actuation moment, and P is the input pressure of air. So the boundary conditions present are clamped-free actuator. The base is fixed, and the tip carries zero bending moment. So the inverse PINN takes arc length and pressure as inputs and predicts the centerline field. The key point is that EI effect and Kp are also chainable. So the network is learning the field and identifying physical parameters at the same time. And the loss combines physics residuals and also BC boundary conditions, sparse shape data, sparse shape data, and tip displacement, and blocked force observations. So for comparison, I also chained a pure MLP with the same input and output variables, but without any physics terms. In the baseline experiment, the PINN identifies the actuation coefficient very accurately and reproduces blocked force very well. This is visible in the parameter trajectory plot and also in the blocked force summary matrix. So for tip displacement, the PIN still outperforms the MLP, but both models underestimate the response at higher pressure. That is because that the mechanics model or mathematical model we used is very hard to depict the large deformation when because the softer this is the intrinsic problem of the softer material itself. So I may like promote the mechanics with more advanced technique in the future. So this result suggests that the remaining issue is not only optimization, but also the fidelity of the reduced order mechanics model, as I mentioned. And this slide is useful because it shows the full centerline shape rather than only one scalar output. At 10 and 55 kilopascals, the PIN captures the centerline chain reasonably, and is visibly better than the MLP. And at 100 kilopascal input, the benchmark shows stronger nonlinear bending, and the current reduced order model cannot fully reproduce that shape. So this was one of the most important experiments in the project. Does blocked force superposition matter? I compared two PIN variants trained on the same data with and without the blocked force loss term. And when blocked force supervision is removed, the identification of KP drops dramatically, and the blocked force prediction becomes very poor. So blocked force observations are not just helpful; they are essential for resolving the inverse problem. And the second formal experiment was about data efficiency. I just compared the PIN and MLP under low, medium, and high data budgets. The low data REDMI is the most informative because that is where physics-informed learning should matter the most. And in that REDMI, the PIN clearly outperforms the MLP in both tip displacement and shape error. And it also shows better stability across seeds. Then is the limitations and the perspectives. So the key limitation is not that the PIN fails completely, but that the current mechanics model is hard to capture the whole characteristics of the soft materials and the soft pneumatic actuator. So I just used a simplified model to reduce the computation difficulty. And the zigzag structure is represented through an effective compliance factor, which is useful but not fully predictive in the large deformation scenario. And the most natural next step is FEM grounded calibration, which would improve the reduced order model and make the inverse identification more realistic. So to make a whole work, a complete work, I may add some more some ground truth experiments by using different soft materials with the same configuration, the same 3D model, and develop a more precise mechanic model. So to conclude, this project shows that a PIN can be used as an inverse model for a pneumatic zigzag soft actuator or more general bending pneumatic actuator. And the strongest result is that the accurate identification of KP and the blocked force response. The most important practical lesson is that force-related observations are essential for identifiability. And the most important modeling lesson is that high pressure shape recovery still needs return mechanics or FEM grounded calibration. That's all. Thank you.